All right, we're streaming now. Am I still audible?
Yes, sir.
All right. Okay, so before we start, just a little question. It's been 3 weeks into this summer school now. What's been your so what's the favorite mathematical idea that you've so far encountered or played with? Anyone? I
I
don't
think,
want to. Yeah.
in my opinion, it would be graphs because I didn't know about it before.
Right. Graph theory, you mean the last week?
Yes.
Okay. That makes sense, yeah. The ideas are unfamiliar, then experiencing them for the first time makes them interesting. Who else? Anyone else? Nothing new, interesting. How about
aside from
okay.
aside from learning a lot of new things like mathematical problems and stuff, I really found interesting the fact that the logic, mathematical logic, how much of math do we actually know?
Mm-hmm.
And I thought about that after, and I still think about that. So I found that really
Right.
interesting, that question.
Yeah, and do you think you have a handle on that problem, or do you think it's still, a bit confusing to think about?
It's still very interesting to think about it.
And is it confusing though?
Yes.
Right. Okay. So this is the last week, and I hope to introduce you to some ideas that you've already probably seen, but in a more intuitive light. So by way of perhaps raise your hands or just speak up, how many of you have ever done something called finding the derivative, or doing something called differentiation?
I have.
I have.
Okay, two hands.
I have.
Okay, so I do see. How about we do the other way around? By show of hands, I want to see how many of you have just never done a derivative before, or just haven't heard of differentiation at all, or haven't done differentiation of basic functions. So for example, if I were to ask the question, is there anyone who would be completely lost when I say something like, when I write something like this on the board and I say, dy by dx, what is anybody seeing this entity for the first time? No, okay. All right, so if I were to ask a simple question, let's say, y equals x squared, what does that, how would you think of this? What would you call it? What's your first thought when you see something like this written down? And I'm not even talking about the derivative right now. Let's get that out of the way. Let's just talk about this thing, this statement, this mathematical statement that I've written on the board. What is the first thing that comes to your mind?
It is a quadratic.
Okay, it's a quadratic. Okay. What flashbacks do you have from your mathematics classes when you look at something like this?
The turning point is the origin.
Okay, so turning point. All right, so you're already starting to talk about some of its properties, but if I were to ask you, what did you mean when you said it's a quadratic, or what did you mean when it's a turning point? What would you say to that?
For one value of y, there are two values of x.
Okay, so you let me write this down. This is 1, this is 2. Another thing, you just said that for one value of y, there exists two values of x. Okay, well, those are really interesting ideas that you've come up with. What else do you remember from your math classes? What is this though? And how do you, what else comes to your mind? So let's change the question. Let's make the question more specific. If let's say you have a relative of yours, or if you have a cousin of yours who's, let's say, 5 years old, and hold on, sorry, there's more participants in the waiting room. Let me let them in. Okay. All right, so somebody looks at this book and your notebook and sees something like this, and they ask you, what is the meaning of this? What would you tell them? Just simply, what does it mean, or why, or even perhaps why are you even studying this?
It's the relationship between two variables.
Right, at its simplest, it's just a relationship that you stated down using some notation. And the nature of that relationship is something that also, was it Hamna who mentioned this? So it's already mentioned as
Yes,
a quadratic
sir.
relationship, right? And so you've already given a name to it, and you've sort of memorized it because you were taught this in class, that this is a relationship, and what we in calculus, of course, or mathematics call functions, or, well, for now it's just an expression, it's just an equation, right? So it relates y, this variable, with x, and it's almost clear, even if I don't tell you, you are almost certain about what's implied here, is that this is some number, and you can plug in any value for x, and you can get out any value for y. You can plug in 1, 2, 4, whatever you want, and you'll get corresponding values. You can actually tabulate these values. If I say, let's put them in a table. So this is 1, then this is also 1. If I plug in 2, that's 4. And essentially what I've written here as x squared is actually basically just a simple multiplication, right? It's not even, a exponent. It's just two numbers being multiplied. And in essence, it's the same number being multiplied with itself. 2 gives 4, 3 gives 9. And essentially, if you start making a table, how many values do you have in your table? How long do I need to make this table to capture every possible value?
Infinite.
Infinite. Okay. And in the second week, we did talk about a little bit about the nature of infinity. So would this table that I'm making, would it be countably infinite, or would it be uncountably infinite?
If you're going to list only the natural numbers, then it's countably infinite.
Mhm.
But if you're going to go into the real numbers, then it's
Right.
uncountably.
Right. So something that you should have asked me when you saw the statement is, what kind of values am I allowed to take for x? So if I write something, if I make a statement, make this statement slightly more complete, I say y is equals to x squared, such that x is a natural number, then there are countably many values of x, and so there will be countably many corresponding values of y. If I were to say these were only the positive integers, then those are countably infinite still. But now and even for natural numbers and even for the positive integers, so what we don't have anymore is something that you mentioned over here, that for one value of y, you get two values of x, because now you've sort of limited the range of values that you're allowed to take for x, right? Okay, and so let's go slightly bit away from this, and let's talk about what else, how else. So there's a table, there's a mathematical equation. How else do you represent a relationship like this? Maybe I can just write it down. Maybe I can say that y is x times x, which is basically just the same thing, but now written down in words. So this is less efficient. This still seems more efficient. This is still less efficient. This is still less efficient. What other ways can you make the statement?
Graph it.
Right. So you could, another way of representing it is just to graph it up. And so you're all familiar with constructing a two-dimensional graph, which is you note down some values and you make a scale. So this is x and this is y. And you note down the scales that this interval represent a width of 1 unit and so on. And so you try to make it as accurate as possible. You use graphing paper if you want. That makes it much easier. 1, 2, 3, 4. And now you start plotting out these values. You can make a rough sketch if you want. So on 1 you have 1, on 2 you have 4. And immediately it's clear to me that the scaling should have been a bit more thoughtful, but I can still make the rough sketch, which looks something like this. I can plot out more values and make this more accurate. And so you're probably all familiar that this looks something like this. And the easier, or if I choose a different scale, you can see this curving out much better. So if I change the scale and I just draw a simple quadratic graph, which I'm sure you've all seen, looks something like this. And of course, if I were to change the statement that, x is now, I've assumed here without even stating it that x takes up any real values, because that's really what we talked about, that in a line there's infinitely many values and infinitely many values of the variable. And so we've sort of out a graph for the y equals x squared relationship. Okay, and so within this relationship, when we say something like dy by dx, what does that mean to you?
The gradient.
Okay, what else? Great. Okay, so you've answered this question with a name. Gradient to me is a name. What does it mean?
The slope.
Okay, again, so answer. It's another word to me. What do you mean by a slope? So if I were to perhaps stand here, what do you mean when you say it's the slope?
The ratio of change in y over change in x.
Okay, so we're starting to get some idea here.
At any point x, a dy dx will give this gradient of the tangent of the graph at x.
Okay, before that, could I have, I heard you rhyme. Before that, what was the statement that you made? Somebody else was making the statement. Can I have that answer again? Just to write it down.
The change in y over change in x.
Okay, so it's a change in y, the ratio of the change in y over change in x. Okay, is everyone in? Okay, I think Rahil is having trouble connecting. Okay, so change in y over change in x, and Rhyme, can I have your answer now at every point?
At every point x, dy dx gives the gradient of the tangent.
Gives the gradient of the tangent
of the graph at point x.
Tangent at the point x of the graph.
You wrote
Okay.
dy dz.
Sorry, that's dx. Just wrote it back. Okay. So then my question is, okay, what do you mean by the gradient and what do you mean by the tangent?
The tangent is the line that meets the curve only once. So the gradient of the tangent is only specific to the point.
Okay, so the line that meets the curve only once. Okay, so first I'm going to pick apart this definition, and we're going to sort of, so whose answer was this? Was it you, Hamna?
Yes, sir.
Okay, so Hamna, we're going to give you a better definition for the tangent today. So whoever taught you this definition, you can tell them that this definition isn't really accurate. And the reason is something like this. Let's suppose I draw this curve. So if I were to ask you what's the tangent at this point, I suppose you would draw something, a line, something like this, which touches it at this point.
Yes, sir.
All right. And if I told you that I've only, of course, this is a two-dimensional sketch that I've made, right? So you really can't see the rest of the curve here. So if this is X and this is Y, and then if I were to fill in the later parts of this curve and I tell you and I show you something like this curve actually goes back up. And you've probably seen graphs like this, right? Do you remember seeing a graph that goes like this?
Yes,
Cubic.
cubic.
Yeah, so cubic graphs sort of look like this if you change their coefficients. And now if I were to extend this line, the definition that you gave me no longer is completely accurate. There's a problem there because you said the line meets that curve only once. The line is over here, it's about to meet it again. So that definition, for me at least, and of course in mathematics, we need it to be precise and we need it to be correct. So how can we change this definition to be accurate about what a tangent is?
Given a domain, so that the curve cannot increase further.
Okay, but how would you decide the domain? So if I were to tell you there's a relationship, and I'm sure you've seen something like this, that y is some function of x, and I give you a few functions, y equals sine x, y equals x cubed minus 4x squared, y equals to 10 log x perhaps, and I can make them as complicated as we want. What domain would you pick so that it's consistent over all functions?
We could say that the tangent is the line that touches 2 points that are infinitely close to each other on a curve.
Okay, so this is, so touches 2 points that are infinitely close. Okay, now I want you to tell me, what do you mean by this idea of 2 points being infinitely close? If I go back to my board here, because if I zoom in, I don't see the other point. So what do you mean? Is it a point that, is it not the same point? So suppose this point was, for being specific, let's call this point x0. Okay. So if 2 points are, how you said infinitely close, they still must, are they 2 different points or is it the same point?
I think that they have to be different because we're measuring the rate of change.
Okay, so if they have to be different, I have this annoying habit, and the real number line has this annoying habit of being infinitely stretchable, right? So suppose if you make those points really close, suppose not even that's close, let's make it even closer. Let's say I put this point right here, okay? And that point then would be somewhere over here. I've actually made this point too thick. If I were to make this, let's see if I pull it. No, doesn't let me erase the point without erasing the curve. Okay, let's pick some other point, right? Let's take this point. Let's try to make it as thin as possible, and let's take another point here. Okay, 2 points. If they are separate, if I draw a line that goes through both of them, then of course I can zoom into this representation as much as I want, because remember when we talked about the idea of the real number line and there being an infinitely many points and actually an uncountably infinitely many points, I can zoom into it as much as I want, and I can make it as big as I want, at least for my scaling purposes, right? Because if they're too close, I want to see them as close as possible. So I can zoom into those points. And once I zoom into those points, the picture that I will get would be something like this. So this curve which had 2 points, something like this, when I zoom into it, what would this section look like to me?
It would look exceedingly like a line. The
It
more you
would
zoom in.
start looking, the curvature would start to look something a little bit flatter to me, at least, if not completely straight as a line. And if I make the points even closer, then you could start seeing a little bit of a hint of a line there, that, you know, it's almost exactly the same as a line. So we treat it as a line, right? So now, but let's say we zoom into it enough and we find that there's still some curvature. And now I draw a line between these 2 points. Does it fit my intuitive idea of a tangent, where a tangent was simply just hugging it once and letting it go? Is this the same intuitive idea that we're trying to capture here?
In this example, there is clearly a lot of space between them, but if it's infinitely close, then yes.
Right. So what do you mean by 2 points which are infinitely close?
They
are
can't get
they
any
two
closer
different-
together.
They can't get any closer together. Okay, so that's, to me, that seems like you're defining just 1 point. How can there be 2 points if there's, so if I ask you if they're very, very close to each other, they're infinitely close to each other, my question is there a gap between them?
No,
So if there's no gap, isn't it just the same point?
no.
Interesting. How would you go about making that argument? That there are 2 points, they're infinitely close, there's no gap between them, but they're still not the same point. So give me an example. If I said x0 equals to 1, can you give me a number which is infinitely close to 1, but isn't 1?
1 plus epsilon.
Okay. And what's the value of epsilon?
It's infinitely small.
Must have some value, right? Is it 0?
No, it's not 0. It's just a little bit more than that.
How much more?
As less as possible.
And how much is that? If I were to, so okay, let's change up the question. We're clearly not getting anywhere here. So another way of representing a number, we've seen this, is to write it as a decimal number, right? So I can represent 1 as 10000, and this goes on. And there's also infinitely many zeros here, but we all know that there's infinitely many zeros here. The decimal point is right over here, and there's infinitely many zeros here, and there's a 1 here. If epsilon, you're saying epsilon isn't, if epsilon were 0, it would be this. If you're saying this is not epsilon, then epsilon must have some other representation. So it's 0.00, but if it's not 0, then it must be different from 0 at some decimal point, right? So which decimal point is it 0 at?
Can I add something?
Sure.
I think what he means by an infinitesimal would be 0.00
Mhm.
and then carried on infinitely, and at the end there'll be 1. But that isn't mathematically rigorous, because you can't say 1 is at the infinite decimal point, because you can't reach the end of infinity. Another argument is 1/3 equals to 0.3 recurring.
Mhm.
And if you times both sides by 3, you
Right.
get 1 equals to 0.9 recurring.
Okay.
Now, if we take away 0.9 recurring from both sides,
Right.
we should get 0, or we get what we mean by epsilon. Either this leads to a contradiction or epsilon equals to 0.
So which one would you be satisfied with?
0.
That epsilon
Another,
is exactly 0?
yeah, and infinitesimals don't exist.
Okay.
Another reason it comes from Zeno's paradoxes. So if I walk across a room,
Mhm.
I must meet the halfway point.
Right. Okay.
Then I must meet the 3/4 waypoint.
Mhm.
Then half of what's left.
Okay.
Then half of that. Then half of that. After I keep walking, either you say that I'm an infinitesimal way away from B, so I can't ever reach B, or that the space left converges to 0 and I am at B. If you say I'm infinitesimal space away from B, then this argument could be repeated for the distance between A and 1/2.
Mhm.
And eventually, then you just admit that motion doesn't exist because I can't move between 2 points.
Okay. I'm really happy, Motion, that you brought up this paradox because I was going to bring it up anyway. So does everybody understand what Ryan just mentioned? That if this, does everybody understand what this paradox is trying to say? And let me just repeat what he said, which is that if I were to travel from point A to point B, if that's my intention, that I start off from A to B, to get from A to B, I must get halfway to A, between A and B. And then I must get halfway between this halfway point and B, which is 3/4, and then I must get halfway, and then I must get halfway again, and halfway again, and halfway again, and so on and so forth. And you keep doing that, and you'll have to basically add up infinitely many small 1/2 plus 3/4 plus so on. And so actually, so between these 2 points, the distance is about 1/4, right? And between the next 2 points, the distance would be 1/8 and 1/16. So because you keep halving the distance, this length would of course be 3/4, and the length from here to here would be like 7/8, and so on. So you have to keep adding. You have to get to another point before you can get to this point. There's always another point that you have to get at. So basically, the idea is there's infinitely many points to get to between A and B. So do you ever really get to B if there's infinitely many points? that you have to get at before you can get to B. And like Ryan said at the end, that if you stick to the position that you actually don't reach B, that there's always some epsilon left over, then you can repeat this argument for this halfway point, that you never really reach the halfway point as well. There's always an epsilon remaining. So how do you even move at all? If I can repeat this argument for any 2 points between A and B, that motion shouldn't be possible. Does that make sense to everyone? Does it, here's a simple question. Does it seem like a paradox, or does it seem like I'm just, it's not really a paradox. I mean, intuitively, we know we can always move between 2 points, right? So does this argument even make sense?
Yes, it does.
So what possible solution do we have to this paradox? Because how do you counter this argument?
Well, coincidentally, I was watching a video relevant to this today. And one, I think, idea that goes around is basically that in the physical world, there is a smallest possible length or time that needs to be traversed, and therefore you don't need to go to epsilon or an infinitesimal.
Right. So that's one way of thinking about this, which is what we have in mind is the real number line, which is infinitely stretchable, and there's always infinitely many points to go through. In the physical world, we may not have a continuum at all. It might just be that it's at the smallest scale, there's the smallest length, and that's a finite length, and it's really, really small, but it's there. And so there's no longer the question of traversing infinitely many points. Because if there is a smallest length, then between A and B, there must always be very, very large number of points of those small lengths, but those will still be finite. There may be a million of them between, let's say, in 1 meter. You might have a million of those, or a billion of those, or a trillion of those, or any large number that you can think of, but a specific number that you can think of, but that's still finite. There's a huge difference. Even if I write down the largest possible number, let's say 10 to the 10 to the 10, and let's stop somewhere, right? And that's still, it's still finite. So maybe that's one way. Does that seem satisfying to everyone, or should there be something else?
I'm not sure that there is a smallest length. There is the
Right.
Planck length, which is the smallest measurable length, but I'm not sure if it is the smallest length.
Right. Okay.
I'd like to add,
Yep.
it doesn't matter about the physical world. We could just repeat the same argument with
Yes.
a number line in abstract math. But the motion is still important in maths. For example, in a limit x is approaching to something, it's changing towards that. The distance between 2 points is shrinking. So you could think of that as a motion in a sense, but if the epsilon existed, then we wouldn't going through. Then we would have the lowest possible length that wasn't 0, and the amount of points between A and B. Then this thing could be repeated. And it also has a problem with convergence. For example, the series you have above, normally we would say the sigma of n equals to 1 to infinity of 1 over 2n equals to 1.
Right. So summation, something like this, 1 over 2 to the n. Something like that?
Yeah.
Okay.
equals to 1. But,
Right.
And another thing I'd just like to add on the definition of a tangent.
Mhm.
We have a formal definition of a derivative.
Right.
So df dx equals to the limit as f of x plus h minus f of x
F of x plus h minus f of x
over
divided by over h. Right.
And we could say that the tangent is the line that has this gradient at
Mhm.
x. But this isn't a very nice intuitive definition. So a better intuitive definition is that it's the instantaneous rate of change at x.
Right. Instantaneous rate of change. And so let me ask you this question. If this is not an intuitive definition, why do mathematicians insist on using this definition? And that's a really important question. And that's a question that you will probably find yourself wondering when you take a few calculus courses, is that when you work your way through a calculus textbook, there's a lot of these unintuitive ideas which we insist that you study, and we sort of this is not even the start, like this is not even the worst of it. Is something that horrifies calculus students, the epsilon delta definitions. Those really get to the and those really seem unintuitive. So, but there's a reason why mathematicians insist on it, and the reason is that the reason is really simple. These are the best way to make things as precise and rigorous as possible. And mathematicians really insist on this because, again, these ideas are a little paradoxical. Even the idea of instantaneous rate of change, when we say change of course means almost between two instances. And so to say that there's an instantaneous rate of change is again almost a bit paradoxical, because when I go back to this curve and when I say what's the difference, what's the change between this when x was x0 and when x was x1, I can point out to two locations and say, okay, what's the change between these two values? And I can see, and I can go across to my y-axis and check the value of y and check the other value of y, y0, y1, and I can see that there is this finite change that's happening, right? And so I can divide the two ratios, y1 minus y0 and x1 minus x0, and it gives me some idea of the rate of change of y with respect to x between two instances. But when we talk about just this one point, and when we draw the tangent line and we insist on calling it the instantaneous rate of change, it's again, the question is, what change are you talking about when you're only talking about just this one point, right? And now one way of answering that could be maybe what we mean is that the tangent, this point and this point, let's say 2 points on the tangent, and we can talk about the rate of change of those points. But of course, the issue there is that this new point that I've drawn is not even on my original curve. So then it's sort of still a bit confusing as to what I mean when I say, when we use a term something as instantaneous change. And so I'll get to now the main thing that Ryan just mentioned, and that's the whole point of this conversation, which is to make things precise, to make this idea as rigorous as possible, to avoid this idea of epsilons and this question, this controversial question about the infinitesimal, which kind of seems to throw up paradoxes. the solution, or rather the best way of talking about these things, is to define this notion of a limit, right? And so how many of you have encountered this idea of a limit and have seen something like limit x approaches a of perhaps some function f of x?
I have.
Yeah, anyone else who's seen this? Okay, yeah, you guys can raise your hands and let me know. I can check it, or you can just speak up. By way of raising your hands, could I know how many of you have seen this idea? Okay, no, just a couple. All right.
I've also
Okay.
seen this idea.
Okay, great. Okay, so the idea of a limit is actually, first let's talk about the intuitive idea, which is when we write something like limit x approaches a, what I mean by this notation is basically the idea that x approaches a, and that's the intuitive idea. That's of course not the precise definition. If I were to tell you that that's the precise definition, you would still ask me, what do you mean by approaches? Because in this idea of approach is still the idea of motion built in. But let's first talk about it, that when I say, when I look at a curve and when I look at 2 points, let's tackle the idea of the tangent, right? So if I were to first look at between these 2 points, right, this x0 and x1, and if I were to take the rate of change between these 2 points, and the way I do that is I draw a straight line between them, and it goes through 2 points, and it's called the secant line, right? And so the slope of the secant line is an approximation of the slope of the tangent line that we draw, right? At least the intuitive tangent line that we draw. And you can clearly see that the secant line is not parallel to the tangent line, which means it must have a different slope. Question, would the tangent line, the red tangent line, have the bigger slope, or the, let's try it in pink, would the pink line have a bigger slope?
The tangent.
Right, so the tangent line clearly is steeper. So we expect that if I were to write these down, the slope at this instant, the slope of the secant line is clearly bigger, or sorry, it's clearly smaller than the slope of the tangent line. And now we try to bring it closer to the tangent line. So let's see if we can do better. Let's try to get closer to that point, and we draw x1, we remove x1 from there and we bring it closer. And now if I draw the secant line, it seems to have gotten steeper, but again, not exactly as the same as the tangent line. If I were to repeat this, then it gets better. If I were to repeat this, again gets better, repeat this, gets better. And it really depends on the distance between these 2 points, which let's call that entity as dx. So right now I'm calling dx as x1 minus x0, and that's really the finite quantity, the distance between them. And what I want is to make this dx approach 0. And so if you can now see, if you could tell me, how would you calculate the slope of this second secant line that I've drawn? If this is x0, x1, and if this point was f x0 and this point was f of x1, how would you calculate these 2 points? Well, let's make it easier. Let's call it y0 and y1 for now. How would you calculate the slope of this pink line?
y1 minus y0 over x1 minus x0.
Right, and that would still be, for now, slope would be less than the tangent line, right? And if I were to rewrite this, and if I were to rename some variables, let's say if I were to call this h, and the distance between x1 and x0, if I were to call that h, then I can replace the denominator and I can call this h. And if I were to start off with the definition that y is some function of x, then I could, of course, over here, I could say y0 is the function evaluated at x0, y1 is the function evaluated at x1. I could again rewrite fx1 minus fx0, and this would of course be the slope of the secant line. And let's compare it to the formal definition that Rime gave us, which was this idea that limit of f of so the limit of f of x plus h minus f of x divided by h, and I've essentially gotten most of it. The only thing that I'm missing is x plus h, which is of course the same as x1. If I take this as x and add h to it, that's essentially x1. So I have this definition, and what makes this important is the idea that we're taking h to 0. We want to know what this quantity will be if we take h towards 0. And that's different from saying we want h to be exactly equals to 0. If I say h is exactly 0 in this representation, what's that going to do?
Undefined.
You would get f of x plus h minus f of x. And if you plug in h equals to 0, you're dividing by 0, which is problematic. It seems like it might blow up or something, or we don't know what's going to happen because it's really, as he said, it's undefined. So we're not plugging in h equals to 0. What we're doing is we're asking the question, what happens when we take h to 0? What does this quantity become?
I do have a question.
Yeah.
When h approaches 0, does it not become equal to epsilon?
When h approaches 0, does it not become equals to epsilon? So I'm going to say I don't know what epsilon is. I don't even need an epsilon right now.
Can we not define infinitesimals in such a way that when a number approaches 0, it becomes infinitesimal?
I don't want to do that because I don't need to. The reason I don't need to do that is because we can make finding limits precise as we want. I'm going to now define the idea of a limit. So let me now give you a rigorous definition of the limit. Okay. So the limit of a function, let's say, when we say limit x approaches a of f of x is some limit L, then we say L is a limit of a function if if and only if. Now I'm going to give you the rigorous definition, which is for every epsilon bigger than 0, there exists delta greater than 0 such that if x minus a is less than delta, then f of x minus f of a is less than epsilon. And what I've just done here is I've defined the idea of the limit of a function. So the building blocks that I need is some functional relationship between x and some other variable. And I have to approach x. I want to approach x. So let's consider the simplest function that I can think of. Let's say f of x is exactly equal. Let's make this slightly different. Let's say f of x is 2 times x. That when x is 1, f of x is 2. When x is 2, so f of 1 is 2, f of 2 is 4, and so on. That's the simplest functional relationship. You can even plot it, and you see that it's a straight line going through the origin, and it's a simple relationship, f of x equals to 2x. And so when I say that, let's suppose I say the following. I say limit of x approaches 1 of the function f of x is simply 2. It's actually really easy to see that if I were to plot a 1 here, and let's say I was coming at 1 from a different side, let's say from the right hand side or from the left hand side, let's say this was my initial starting value 1.5, or let's say it was 2, and I wanted to know what value did this function approach as I took the value of x from 2 to 1. So at 2, I know that this value is going to be 4. At 1.5, what's this value going to be? If it's simply f of x equals 3. Sorry, f of x equals 2x. So what's the value at 1.5?
3.
It's 3. Okay, let's get as close to it as possible. 1.25, what would that give me?
2.5.
2.5. I try to get even closer, let's say 1.01. What would that give me?
2.01.
2.02. Right. So I can see now it's starting to become clear to me that when I take x towards 1, this function value, this f of x, is going towards 2. And now it's easy to see it from the graph, right? It's clearly getting closer and closer to this point. If I make it 1.0001, it will become 2.0002. So that idea is clear. But what about these weird symbols that I've written here, this definition? How does this definition fit in? And the way to see that is to see what is happening to the range when the range of these values when I get closer. So let's say here the value of a x minus a is less than delta. A is basically the value that I want to approach. So a over here is 1. Right? That's the value that I want to approach, because notice in this definition, I was approaching limit x approaches a of the function is equals to L. So a is this value that I'm approaching. So a equals 1 and L equals to 2 here, as that's my limit that I want to see here. And the way to see what's happening in this definition is to first understand this idea that what these two things are doing are basically bounding how far you are from your from A, how far x is from A. So this is the value that you're moving around, moving closer to A. So initially it was 2. So the distance between x and A. So this distance was, what's the difference when A equals to 1 and x equals 2, then the difference was clearly equals to 1. So delta here is equals 1. And when this distance is equals to 1, what was the corresponding distance between my function value at x, which is f of 2, f of 1, right, which is 2, and the function value at a, which is 4 right now. So this is the range initially. Okay. And now let's play around with this range. If I were to make this range smaller, you can see that this range also gets smaller, right? If I were to make my new value, if I were to approach 1, when I say approach 1, I mean I take x closer to 1. When I make this range smaller, this range becomes smaller as well. When I make this range even smaller, let's say 1.25, this range becomes even smaller. And so now let's read up this definition. This range is denoted by delta, and this range is denoted by epsilon, right? And so what we really want is what I mean by the definition of a limit, that this limit is exactly 2, is that I can make this epsilon approach 0. I can make it as small as I want. And if I wanted to make it as small as I want, let's say I want to make it 0.0001, I can find a corresponding delta here. So if I wanted to make my value become, if I wanted to make f of x become 2.00001, then what's my epsilon here?
Can you show me the number?
4 zeros.
Yes, 0.000005.
Right, 0. Epsilon.
Oh, okay. Yes, 1.
So for now, the way I've defined it, it's just 1, right? Because the distance between these is clearly less. So I want the distance to be less than epsilon, which is 0.0001. Question is, can I find a delta? That is there, can I make this x approach it so close that this is epsilon close to 2?
Yes.
What would that delta be?
Epsilon divided by 2.
So
0.
So if delta is epsilon divided by 2, so that's like 0.000005, right? And so what you're essentially saying is that x minus a, when I write this as less than delta, right? The absolute value of x from this point A, if this is 1 and this is 0.000005, then the value that I have to choose for x is 1.000005. If I were to choose this value 1.005, then it's exactly equal to the delta. So if I want to make epsilon smaller than this value, I just have to pick some value which is smaller than this one, which is I can make, perhaps if I want to choose a smaller value, that could be simply I could replace this 5 with a 4 or a 49999, just as long as it's smaller than this value. And so this is exactly what this definition, this weird and terrifying definition of a limit, is trying to capture, which is that it doesn't matter what value you're taking for epsilon, you will always be able to find a corresponding delta such that both of these conditions are satisfied. And if you want to make epsilon as small as possible, then that is the delta that you need. Does that make sense? Any questions on this?
This definition only defines continuous functions.
Right. Sorry, hold on. Have I made a miss? Did I move too quickly to the definition of a continuous function rather than moving to the definition of a limit. Okay. F of x.
Minus L.
Right. Sorry. I should have wrote that as minus L. Okay. So this is not f of a. This should be L. Right. We're not considering the value of that function. What we're saying is L is basically equals to 2. So far, we're not considering what the value of f of 1 is at that point. We don't need the value of that function to be equal to that. I could, and let me make this more precise, why I don't need the value of 1 is I could actually leave a hole here. I could say that f of 1 is undefined and make it a discontinuous function. And the way to do that is very simple. Let me show you a discontinuous function which looks exactly like this. Let's say I redefine f of x as 2x times x minus 1 over x minus 1, let's say. And so now the function is 2x squared minus 2x over x minus 1. This function is going to be problematic at x minus 1 because as soon as I plug in 1, it's going to become discontinuous. It's going to be undefined. So it's actually exactly the same, but with a hole for x equals 1. If you do some algebra and if you were to cancel out these two factors, then you can see that essentially this is equivalent to 2x, except at the point x not equals to 1, right? So that's why we don't even need the definition. We don't even need the value of the function at that point to define what a limit is, because you can see even in this, even the approach idea is still relevant. If I were to approach x from this side, right, then it's still, if I were to draw the y-axis here, and this is the value 2 here, still approaches 2. If I were to approach it from this side, then it still approaches 2. What happens at that point is irrelevant. Does that make sense? Questions? So is everyone with me, or has everyone sort of lost what I'm talking about? Are there any questions on chat? Anyone? Okay, let's see who is here. Okay, Zainab, Sarah, is it clear what I just mentioned right now? Is the definition of the limit clear to you? Hamna, Fatma. Am I audible?
Yes.
Okay. Abdul Ahad, are you here?
Yes, sir.
All right, so can you tell me if the definition of a limit is clear to you? Sorry?
To be honest, not that much. I'm just trying to keep up and understand everything I'm looking at.
Right. So at what point did I lose you?
Well, no, not lose. Like, I think I did get most of it. I just, it's hard to grasp.
Mhm.
Well, remember. I just looked this over
Okay.
more later.
All right. Is Mariam still here? Fatma? So if you don't get this definition, you can think about it later if it doesn't make sense to you. I want to recap what we just did. The reason we need this definition is we want to make the idea of approach very precise, right? This idea of this movement, this approach, the movement goes away from this whole thing as soon as you start talking about these bounds that I've placed here. So this approach idea is no longer required. You don't need to use words like moving towards it and approaching it. And even if you use it, you are sort of secure at the back of your mind. You know that when you use these terms, they're actually backed up by these mathematically rigorous ideas of this epsilon delta definition of a limit. That it is a limit, the limit of that function is actually given by this definition. So as an example, let me say, when I say something like the limit of x approaches 1 of 2x times x minus 1 over x minus 1 is equals to 2, I am not plugging in the value of x equals to 1 here. And the reason why I'm not doing that is because in the denominator, that would create a problem. If I plug in x equals to 1, I have nothing, but it's a well-defined function. It's clearly 2x squared minus 2x over x minus 1. Other than x minus 1, other than x equals to 1, this is a reasonably well-defined function. I can plug in any other value closer to 1. So how about you take out Google or plug your calculators and plug in some value close to 1. Let's say 1.0001. What value do we get for that?
2.
1.0001, you get f of x equals 2.
Yes.
If I
2.0002.
So you
Yes.
should get 2.0002, right?
Right.
And if you were to take x equals to 1.000001, what would you get? You should get 2.000002, right? The only problem is that you can't plug in f of 1 here. As soon as you do that, the denominator creates a problem. It's a zero division error, and you're left scratching your head. But there's still clearly this pattern, this behavior near 1 is still the same as it was for 2 times x. The same behavior that you had for 2 times x is the same behavior that you have for 2 times x minus 1 over x minus 1, right? And so this behavior that's same is what I want to capture here in this definition, is that when limit x approaches 1 for 2x, or when limit x approaches 1 for 2x times x minus 1 over x minus 1, both of these limits are actually exactly equal to 2, even though the function is not defined at that point. I don't need to define the function at that point, because I can tell you that no matter how close you want to get to 2, you can do that. If you want to get to, let's say, 100 decimal places close to 2, that is, this is how close you want to get to 2. I can get you that close by picking an approximate delta. I would choose, if this is what you want f of x to be, I can choose a corresponding 1.000 and a 0 and a 5 here, and I'll get as close. When I plug this in inside my function, it's going to give me 2.000, 100 zeros, and a 1. I can get as close to 2 as I want. And that's really what's encapsulated in this notation, limit x approaches 1, even though f of 1 isn't defined.
I'd like to add, if you go back to the definition,
Right. Sorry, where was it? Yeah.
yeah, what this is saying in math is basically the function f of x approaches at the limit L near A if we can make f of x as close to L as we like to, by requiring that x be sufficiently close to but unequal to A.
Right. Yeah, exactly. That
And
this
this can
problem.
be this can be just transformed into this very easily, since f of x minus L modulus is the distance between these two, is the metric in R.
Right. I'm sorry, what was your comment? I seem to have missed.
I said f of x and minus L is the distance between these two.
Yeah, exactly. Right. So this is what we are referring to as the distance. So f of x minus L, this absolute value, is when you look at the real number line, right? When you want the distance between 2 points, you subtract them and then you take the absolute value. And that gives you an idea of how far the 2 points are from each other. So this ugly little inequality that I've written here is basically telling you that from L, f of x is less than epsilon away, that whatever distance this is, this distance d is going to be less than epsilon. And that's true, this limit exists if you can find a corresponding delta for every epsilon that you have, right? So this distance right here, this distance is denoted by epsilon, and this distance is denoted by delta. And what we're really doing is, well, if you plug in the definition here, this is saying 4 minus 2, that's my limit for L equals 2. That's, I've made it, so this is less than epsilon. And right now, what is it? Right now it's 2. And I can choose a delta. And in my case, that delta is equals to 1. If I want to make this distance less than 2, just make the distance delta less than 1 and I'll have it. If you want to make it less than 1, just choose delta as half and so on. And you can keep doing that for this specific function. You can't do that. However, let's give you a counter example. Let's give you an example where you can't do this. Let's suppose you have a discontinuous function, right? Let's say you have a function that looks like this. It's defined like this. And then it's something like this, right? So what we're saying now is that this function, and let's call this value, let's say this is 3, and let's say this is 2. Now,
is the tangent function also discontinuous?
Right, so let's get to that. I haven't gotten to that yet. So let's talk about what we mean by the tangent function. Okay, but for now, let's talk about this discontinuous function. If I were to approach 2 from the left-hand side, and if I were to check the values of my function, I would start seeing, and let's say this value is 4. And if I were to start off here, I would get this value. If I were to get here, I'd get this value. Here, get this value. Here, get this value. If I were to approach, as I say, right? So now I'm approaching, there's actually a difference now in where you're approaching from. If you're approaching from the left, now it seems I'm going to approach the value 3 if I were to plug this inside my function. And if I were to approach it from the right, I would be approaching the value 4. And so now the question is, what is the limit of this function? Is it 3 or is it 4?
The limit as x approaches 2 isn't defined, but the limit as x approaches from the left and the right are defined.
Right, so right now we haven't defined the left-hand limit and the right-hand limit, right? What we've defined is simply the definition, which is that for every epsilon greater than 0, delta, there exists a delta greater than 0 such that if x minus a is less than epsilon, and sorry, x minus a is less than delta, then f of x minus L is less than epsilon. So let's take an example. Let's assume that we want the limit. Let's say we thought the limit was 3. So if the limit was 3, right, and I have a corresponding epsilon, so let's say I wanted to make this distance between whatever f of x I want and this limit 3, I want to make it smaller. Let's say epsilon for now is 0.5. Can I find a corresponding delta for every possible epsilon such that the absolute value is always less than 0.5?
You can't, because let's say you find the delta such that x minus 2 mod is less than it, maps onto f of x minus 3 is less than epsilon.
Right.
You would only have x minus that 2x is between 2 plus delta and 2 minus delta.
Right. So this equality simplifies this inequality. If you simplify it, when we say this, what does this mean? It means basically the distance of x from 2 is less than delta. That means it could either be on this side. Let's say this is delta. So it could be 2 plus delta. Anything less than this could be x. Or if we go to the other side, let's make delta here. Then anything less than 2, so 2 minus delta, anything within this range is an acceptable x for me, right? Okay, go on, right?
If you consider the map, then you will have a part which is within 3 and a part that's above 4. And the definition says f of x minus L, which is 3 here, has to be less than epsilon, but it's only, but there's a space between 4 and 3 where it's not.
So I've picked epsilon to be less than, I've picked it to be 0.5. So I want the distance between my function value and my 3 to be less than 0.5. Was I able to guarantee it within this delta?
No, because there's a part outside 1.5 within where.
If this is 3, then maybe I can satisfy it for this part. Maybe this distance could be less than 0.5. I don't know. But this part definitely can't be less than 0.5, can it?
No, it's more than 1.
It's more than 1, definitely. So if the limit can't be 3, can I claim that the limit is 4?
it's the same argument for that.
It's
No.
the same argument. If I claim that this is my limit, well, then the other side is the problem. I can't approach this value. This distance, this discontinuity has stopped me from making that progress towards 4. However, if that wasn't the case, if this was a function that looked like this, even if the function value was not defined at that point, then I would have no problem for any epsilon. If I wanted to be as close as possible to this point, let's say this L, if I wanted to be close to this point, I could make a map and get as close as possible. I could find a delta that would get me as close as I wanted. In this case, not really. So the limit doesn't exist in this. And so this part is the rigorous technical definition of the limit. And the idea, what we want to see by the graph is really the intuitive idea, is that what's the value? If you want to see what's the value is, you can actually, if you want to see it, just plug in the values and try seeing what the value is. Right? And plug in as close as possible, and you would still get the idea. And in calculus, we see a few rules on how to calculate limits, right? So simple rules like if I have the limit x approaches a of f of x plus what was limit x approaches a of f of x plus g of x, well, we can use an argument, a mathematical argument, to show that it's actually limit of x approaches a of the first function and add it separately to the function, the limit of the function g of x. So that's a simple rule that we can use. So if you know the limit of 2 separate functions, you know exactly what the function limit is going to be. If you know what the function of limit x approaches a of f of x is, right, then even if I multiply it with a small value or a large value, doesn't matter, by a scalar value that doesn't change, by a fixed constant value, then it's nothing but that scalar value being multiplied by the limit of the function. So you only have to sort of look at, sort of in your calculus courses, you'll go through these definitions and you will work out them rigorously. But as soon as you know them, then as soon as you have a background, a technical understanding of why this is precise, then later you can start being, a little bit careless with the notation and the terminology, as long as you're aware that there is a strong technical foundation for these ideas. Okay. All right, and so let me just give you a sort of list of ideas that calculus leads us into. Is we sort of start off with this idea of the limit and the derivative, and I've run out of time, so I'm going to pick up with the derivative in the next section, and integrals. And it's really, I want you to see calculus not as a subject in itself, but it's sort of really your key. It's the gateway, and it's a toolbox to many techniques. It's a set of techniques that allows you to do much more advanced mathematics. It's really a gateway towards, let's say, pure mathematics like real analysis, like complex analysis. It's also a gateway towards higher calculus, which involves differential equations, which I hope to give you an idea in the third session. And there's lots and lots that you can do with calculus. There's approximations and there's estimations, there's numerical methods. It's a gateway to really any higher, even statistics uses several tools from this calculus. So you take up any program, an undergraduate program, and you're bound to see calculus as one of the first mathematical courses that you're expected to know, right? And this toolbox, it allows you to, take out derivatives, have an understanding of the foundations of these ideas, really define what a derivative is, right? So dy by dx is really, if you want to define it, it's really this limiting idea becomes really important. Limit of x approaches a of f of x, h approaches 0 of f of x plus h minus f of x. over h. So I now want you to, really look at this definition and see why I'm not plugging in h equals to 0. And this notation is allowing me to sort of approach it as close as possible, but avoid any paradoxes of epsilon and of, infinitesimally small, or if dividing by 0, it allows me to bypass all of those issues and to just ask myself, well, what is the limit here? And earlier we were just talking about the limit of a function. Now I'm talking about the limit of this whole thing. So what would that mean? Okay, so think about that. And if you have any questions from what I've said, if you want to, have a deeper dive at this idea of these limits, feel free to ask them, because these are really confusing ideas. Our students just, struggle for their entire semesters about these epsilons and delta definitions, but they're really there to just make it precise. The idea of approach is still the same. Okay. All right, let's call it a day there. Any questions? No. All right. See you all on Wednesday. Have a good day.